In this section, we're going to be looking at functions, and then more specifically, linear functions. So what we have is some information on crickets. Crickets chirping seems to depend on the temperature. The warmer it is, the more they chirp. The colder it is, the less they chirp. So we have a table of temperatures in Fahrenheit and number of chirps in 15 seconds. And we can actually use this information to talk about a function. When something depends on another thing, we end up with this function. And we'll get into more detail of what it means to be a function. But there's different ways to relate this relationship. One's a table, one's a mapping diagram, and one's a graph. So table is pretty easy. We'd have our temperature and our chirps. So this could be the temperature in Fahrenheit. And this is the number of chirps. And we had 50 degrees had 10 chirps, 60 degrees had 20, 70 degrees had 30 chirps, and 80 degrees had 40 chirps. Now in a mapping diagram, we represent it very similarly. This would be your temperature, and this would be your chirps. But you're showing which ones match up. So 50 goes to 10, 60 goes to 20, 70 goes to 30, and 80 goes to 40. On a table, the one we're depending on, the temperature, would be our horizontal, and the chirps would be our output, so that would go up there. So I'm going to count by tens, 40, 60, 80, 10, 20, 30, 40, 60, 80. So when I had a temperature of 50, I had 10 chirps. Temperature of 60, we had 20 chirps. 70, we had 30 chirps. 80, we had 40 chirps. And so forth. Another way to represent a function is with a formula or an equation. So let's call temperature T and chirp C for fun. How are they related? And it's pretty easy to see from the table to get from 50 to 10, 60 to 20, 70 to 30. Looks like we're subtracting 40 each time. So the chirps will equal the temperature minus 40. Another way you might see it with IB is they sometimes use this. This means that C depends on the temperature minus 40. Yet another way is with function notation. C of T, in other words, the chirps depending on the temperature. Now, being a function means that the first component is matched up with exactly one of the second component. So 1 to 3, sometimes it's easier to see it in the mapping, that each one of these can only go to 1 on that side. On the graph, you'd have something like that. All of them are separated. Now, not a function. Notice I only really have 3 things in that original column. And that the 1 is going to the 3 and the 4. That makes it not a function. Even if 2 is only going to 7, we still have a lot of non-function behavior going on when one of these values go to more than one of those. So here I have 1 going to 3 and 4, 2, 1, 2, 3, 4, 5, 6, going all the way up to 7, 3 going to both 9 and 10. So there was something called a vertical line test that is also failing when you have non-functions. Now, just a reminder, what do we call the input and the output? The input is called the domain, and the output is called the range. Now let's talk a little bit more about function notation. Function notation. F of x equals 3x squared plus 2x minus 5. This x is the placeholder for our input, our domain. You can think of it as a box that gets filled in with whatever is placed in there. So if this had an x, then we have an x and an x. If it has a 3, then we are literally going to plug in 3 and a 3 every time there was the box. That would give me 9 times 3, which is 27. 2 times 3 is 6. 27 plus 6 is 33 minus 5. Wait, 27 plus 6 is 33 minus 5, that should be 28. Okay. What about the negative 4? Again, it goes in for each of those input values. That's just a placeholder. This is a specific input value. Negative 4 squared is going to be 16. 16 times 3 is 48. 2 times negative 48 is negative 8. And then minus 5. This should be a 35. Now what if they change it to an A? Again, that x was just a placeholder. This means to put an A everywhere we had the box. Even if it was a symbol, it goes in everywhere we had the box. Even if it's an expression, it just goes in everywhere we had the box. Now we could make that prettier, but for the sake of time, we're going to stop right there. But we're going to use this moment to look at domain and range, especially using a graph for the domain and range. The domain are the x values that are being used. So in this picture, we'll notice that it starts here at negative 2, and our x values end here at 2. So our domain would be negative 2 to 2. For our range, we're looking at y values. So if we look, one way to do this is with sticky notes. That's as far up as it goes, and that's the lowest it goes. So it's from 0 to 2. 0 is less than or equal to y, which is less than or equal to 2. On this next picture, if we're looking at the x values left and right, that arrow means we're continually going, and we're going further and further to the left, further and further to the right. There is no stopping point, so this could be all real numbers. Again, for the range, it's going up and down and never stopping. The range would be all real numbers. The domain on this next one, the arrows imply that it keeps going and going and going and going, which would include going to the left and the right forever. So the range and the domain would be all real numbers. But for the range, there's nothing below this. So it starts right there at 2 and keeps going up and up and up. So that would be all the y values greater than or equal to 2. The next graph is a discrete graph. We just have a series of points. So we will have listed out domains and ranges because it is not connected or continuous. Our domain, I would look for the x values, and I like to write them from least to greatest. So where's the first one? It's at negative 4. Then I have another one at negative 2, 0, 1, 2, 3, 5, 7, and 9. For the range, my outputs, my y values, I start with the smallest one. So I'm looking and looking, 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 looking. Here's this first point, negative 2. It's the smallest y value. Then negative 1. Then I have this little gap up to 5. And then 6. And then 7. So those would be the outputs, the y values that are being used. Now, there are a few more for you to practice, but I'm running short on time. What if we're given a function? Well, one thing you can do is actually look at it in the calculator and find the domain and range from there. Or you can remember back to a little bit of Algebra 2. Squaring something. Well, what kind of numbers can I square? Oh, I can square any number, so all real numbers. Now the negative x squared, let's think about what that would look like. And you can look on your, make your calculator. That's negative, so it's flipped. It's going like that. So the y values have to be less than or equal to 0. The next one is y equals 2x plus 3. That is a line. So the domain would be all real numbers. The range would be all real numbers. Y equals 2 to the x. If you look at that in the calculator, you're going to see something that looks something like this. And let's think on that one. Domain. Well, it's going off to the left and it's going off to the right, so that's all real numbers. The range. What are our outputs? Well, if you remember, our outputs are going to be y's that are greater than 0. This one has an asymptote. And if you look on your calculator and looked at the table, you'll see that it never actually reaches 0. Square root of 4 minus x squared. If you looked on the calculator on this one, you would see something that looks like this. The x values are actually going between -2 and 2. And if you looked at the table, you would notice that there's no other ones there. The y values are going between 0 and 2. Y equals 1 over x minus 2. If you looked at that in the calculator, you would see something like this and this. Something weird, whoops, yeah, I had it right, x minus 2. Something weird is happening when x is 2. We're getting what is called a vertical asymptote because you can never divide by 0. And 0 only happens when x is 2. So x can never equal 2. If we notice also, it's never actually touching the y-axis. So y is not ever going to be 0. On this last one, this one looks something like that on the calculator, starting at 1 and going off. So it's the x values that are greater than or equal to 1. You also notice that the graph is only above the x-axis, so the y values are greater than or equal to 0. Now, the last problem I want to look at, and there were some more writing equations of lines from graphs, but I'm going to kind of skip that for the sake of time, and we are going to look at this situation. Suppose you are suspending weights from a spring. The length of the spring is a linear function of the amount of weight suspended from it. So, function is length with any weight. So I'm going to make a little table here. We've got weight and length. When you have 20 grams of weight, the length was 7.5. And when you had 80 grams of weight, you have 15. So when we're writing an equation, the first thing we want to do is find our slope or our gradient. So I'm going to take y value minus y value, 15 minus 7.5, over 80 minus 20. And this ends up giving me 7.5 over 60. Now when I put that in the calculator, I got something very strange. 7.5 divided by 60. So let's talk about what to do then. 7.5 divided by 60. Gave me a weird fraction, and it's okay to leave it with that fraction, but we can also see if that would be a pretty fraction. So I'm going to hit Math, and the first option is to transfer that to a fraction. Oh, it's 1 over 8. That makes it a lot prettier to look at, especially if I was going to need to graph it or anything. Now, y equals mx plus c according to the IEP papers. What you do is you plug in an x and a y value. So here's an x and a y. And we plug in our slope. Our slope is 1/8 of the x value plus c. 1/8 of 80 is 10. So 15 equals 10 plus c. That means c has to be 5. So our equation, whoops, I almost said y. It's really L because we're talking about length, equals 1/8 of the weight plus 5. Now the next part is can we find out, answer questions based on a linear function. How long is the spring when no weight is attached to it? In other words, when our weight is 0. Well, that should be 5. And that is 5 centimeters. We want to make sure we use our units properly. How long is the spring with a weight of 120 grams? Well, here's where the weight goes. And we ended up getting 1/8 times 120 plus 5. I got 20 centimeters. So you can use linear functions to answer questions.